Preparing for a guidance, navigation and control (GNC) engineer interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you choose between Euler angles, quaternions, and direction cosine matrices for attitude representation? An attitude representation defines how I describe vehicle orientation for estimation and control. Euler angles are intuitive but suffer gimbal lock and singularities. I typically use quaternions for propagation and rotation, normalizing them after integration, while converting to Euler angles only for display. Direction cosine matrices are redundant but useful for validation. My choice depends on computational cost, numerical conditioning, and interface requirements. I always document frame conventions and multiplication order. While answering, compare singularities, computational cost, numerical stability, interpolation, normalization, frame conventions, and practical use cases for estimation, control, simulation, telemetry, and operator interfaces. Question 2. What does observability mean in a navigation system, and how would you evaluate it? Observability means determining whether measurements contain enough information to infer the system state. I build the measurement model, linearize it along representative trajectories, and examine the observability matrix, singular values, or Gramian. Poor rank reveals unobservable states such as certain biases or global yaw without an external reference. I also test realistic trajectories, sensor timing, and noise because theoretical observability can be weak or practically useless under limited excitation. Make sure to cover state distinguishability, measurement models, observability matrices or Gramian analysis, local versus global observability, sensor geometry, unobservable modes, and practical simulation-based validation. Question 3. Explain the difference between guidance, navigation, and control in an autonomous vehicle. Guidance decides where the vehicle should go, navigation estimates where it currently is and how it is moving, and control converts desired motion into actuator commands. For example, guidance generates a waypoint or acceleration profile, navigation fuses inertial and external measurements, and control tracks the resulting attitude or velocity target. I keep interfaces explicit, timestamps, frames, covariances, and validity flags. That separation enables independent testing while preserving closed-loop performance. In your answer, distinguish trajectory generation, state estimation, and actuator command generation. Explain their interfaces, update rates, feedback loops, coordinate frames, and how errors propagate across the three functions. Question 4. How would you design an extended Kalman filter for inertial and GPS fusion? I would define position, velocity, attitude, accelerometer bias, and gyro bias in the state, then propagate them using inertial measurements and a quaternion attitude model. GPS position and velocity provide measurement updates through a linearized observation function. I tune process noise from sensor specifications and motion uncertainty, use Joseph form covariance updates when needed, and gate innovations against expected statistics. I also handle delayed timestamps, outages, and filter reset behavior explicitly. Be sure to mention state selection, continuous time dynamics, discrete propagation, Jacobians, process and measurement noise, covariance updates, initialization, outlier rejection, and consistency testing such as innovation statistics. Question 5. What causes Kalman filter divergence, and how would you diagnose it? Filter divergence occurs when the estimator becomes overconfident or its predicted state consistently disagrees with reality. I inspect innovation residuals, normalized innovation squared, covariance eigenvalues, sensor timing, and frame transformations. Common causes include underestimated process noise, incorrect bias models, stale measurements, poor initial attitude, and faulty Jacobians. I reproduce the issue with recorded data, add assertions and plots, then correct the model before applying inflation or adaptive noise as a temporary safeguard. Focus on incorrect models, poor initialization, bad covariance tuning, linearization error, timestamp problems, numerical instability, outliers, unmodeled dynamics, innovation analysis, and systematic isolation using simulation and logged data. Question 6. How would you linearize nonlinear vehicle dynamics for controller design? I write the nonlinear dynamics as x equals f of x and u, select an operating point or reference trajectory, and compute A and B Jacobians around it. For attitude systems, I prefer small angle error states rather than subtracting quaternions directly. I verify derivatives with finite differences and compare the linear model against nonlinear simulation for expected perturbation sizes. If the operating region is broad, I use gain scheduling or nonlinear control instead. Discuss equilibrium or trajectory selection, perturbation variables, analytical versus numerical Jacobians, time-varying linearization, validity limits, coordinate choices, and verification against nonlinear simulation. Question 7. Compare PID, LQR, and model predictive control for a flight control problem. PID is simple, transparent, and effective for well-separated loops, but tuning becomes difficult with coupling and constraints. LQR uses a linear model and cost function to balance state error against control effort, making multivariable regulation systematic. MPC predicts future behavior and handles constraints directly, but requires more computation in a reliable model. I might use PID for inner actuator loops, LQR for attitude stabilization, and MPC for constrained trajectory tracking. Cover tuning effort, model dependence, multivariable coupling, constraints, computational requirements, robustness, interpretability, and when cascaded PID, LQR, or MPC is appropriate. Question 8. How would you design a cascaded attitude and position controller for a multirotor? I would use an outer position loop to generate desired velocity, a velocity loop to generate acceleration, and an attitude loop to align thrust with that acceleration while tracking yaw. Each inner loop must be substantially faster than its parent, with actuator limits propagated outward. I include thrust saturation, integrator anti-windup, tilt limits, and graceful handling of unavailable position data. I validate the cascade with hover, aggressive maneuvers, disturbances, and motor failures. Mention loop bandwidth separation, position to velocity and velocity to attitude commands, thrust vectoring, yaw handling, actuator allocation, saturation, anti-windup, and frame consistency. Question 9. What is sensor calibration, and how would you calibrate an IMU? IMU calibration estimates errors that distort measured acceleration and angular rate. I model bias, scale factor, cross-axis misalignment, and temperature effects, then collect carefully designed static orientations and dynamic rotations. I solve the parameters with least squares or nonlinear optimization, checking excitation and conditioning. After calibration, I validate residuals across temperatures and motion profiles, while allowing the navigation filter to estimate slowly varying biases online. Correct axis conventions are essential. Be sure to discuss bias, scale factor, misalignment, axis signs, temperature dependence, static and dynamic data collection, parameter identifiability, calibration validation, and online bias estimation. Question 10. How do you handle actuator saturation in a flight control system? Actuator saturation means the requested command exceeds available authority, so the actual vehicle response no longer matches the controller's assumption. I constrain commands before allocation, prioritize essential axes when necessary, and use back calculation or conditional integration to prevent windup. I monitor persistent saturation and trigger a degraded mode or return strategy. Allocation should consider efficiency and faults, while rate limiting prevents abrupt commands that create unnecessary saturation. In your answer, cover physical limits, control allocation, priority handling, anti-windup, command shaping, rate limits, degraded modes, saturation monitoring, and the difference between temporary saturation and loss of controllability. Question 11. How would you perform control allocation for a redundant actuator system? I map actuator commands to body forces and moments with an effectiveness matrix. For redundancy, I solve a constrained weighted least squares problem, minimizing command effort or power while meeting the requested wrench. Null space freedom can balance thermal load or preserve reserve authority. The allocator must detect failed or degraded actuators, update its model, and prioritize controllability over efficiency. I test rank, saturation, transitions, and fault cases in both simulation and hardware. Discuss actuator effectiveness matrices, weighted least squares, null space exploitation, constraints, efficiency objectives, failed actuator reconfiguration, saturation handling, and validation across the full operating envelope. Question 12. What is the difference between body, inertial, navigation, and sensor frames? A body frame moves with the vehicle, an inertial frame is approximately non-rotating, a navigation frame is locally defined for position and velocity, and a sensor frame follows each instrument's mounting. I maintain explicit transformation functions and never rely on implicit conventions. Every vector carries a documented frame and timestamp. I verify chains using simple cases, such as level hover and pure yaw, because sign or rotation order errors can otherwise look like controller instability. Make sure to explain frame origins, axis conventions, active versus passive rotations, earth models, transformation chains, timestamps, and how frame mistakes appear in navigation or control behavior. Question 13. How would you estimate a vehicle's state during GPS loss? During GPS loss, the inertial solution continues propagating position, velocity, and attitude, but uncertainty grows rapidly, especially from accelerometer bias. I would use available aiding such as vision, lidar, radar, airspeed, magnetometers, or terrain data, depending on the vehicle and environment. The estimator should increase covariance, declare degraded navigation, and coordinate with guidance and control. On GPS return, I gate measurements and blend or reset carefully to avoid command discontinuities. Cover inertial dead reckoning, drift sources, alternative aiding sensors, estimator mode transitions, covariance growth, observability, fault detection, safe behavior, and reacquisition without discontinuous state jumps. Question 14. How do you design and validate a fault detection and isolation system for GNC sensors? I generate residuals from estimator innovations, redundant sensor comparisons, and physics-based checks such as acceleration limits. A single threshold is rarely sufficient, so I combine magnitude, persistence, rate of change, and contextual checks. Detection must distinguish noise from genuine faults, while isolation identifies the failed sensor and changes estimator weighting or configuration. I test missed detections and false alarms using injected faults, boundary cases, timing failures, and realistic environmental disturbances. Mention redundancy, residual generation, innovation gating, temporal persistence, cross-sensor checks, false alarm trade-offs, isolation logic, voting, failover behavior, and safety case evidence. Question 15. What is gain scheduling, and when would you use it instead of one fixed controller? Gain scheduling uses controllers tuned for different operating conditions, such as airspeed, mass, altitude, or configuration, and interpolates between them. I use it when vehicle dynamics vary too much for one linear controller but remain structured and measurable. Scheduling variables must be reliable, transitions need smooth interpolation and hysteresis, and each region requires margin analysis. I validate the complete scheduled system, not only the individual designs, especially near boundaries. Discuss changing dynamics, scheduling variables, interpolation, stability between operating points, hysteresis, coverage, validation, and alternatives such as robust, adaptive, or nonlinear control. Question 16. How would you account for time synchronization and latency in a closed-loop GNC system? Latency changes the effective phase of the feedback loop and can destabilize an otherwise well-tuned controller. I timestamp measurements at acquisition, synchronize clocks, measure transport and computation delays, and preserve those timestamps through processing. The estimator can propagate to a common time, while the controller may predict the state to actuation time. I quantify end-to-end delay with instrumentation, include it in simulation, and reduce bandwidth or redesign gains when margins are insufficient. Be sure to cover sensor timestamps, clock drift, transport and computation delays, buffering, prediction, delay compensation, hardware triggering, and closed-loop stability impacts. Question 17. How would you verify and validate a GNC algorithm before flight testing? I start with traceable requirements and testable acceptance criteria, then build unit tests for math, frames, Jacobians, and boundary conditions. Software in the loop explores broad Monte Carlo cases, while hardware in the loop exposes processor timing, interfaces, sensor behavior, and actuator limits. I inject faults, delays, dropouts, and extreme environments, then review coverage and logs. Flight testing proceeds incrementally. Bench, tethered, constrained maneuvers, envelope expansion, and independent safety monitoring. Cover requirements traceability, unit and integration tests, Monte Carlo analysis, software in the loop, hardware in the loop, fault injection, formal checks where appropriate, flight envelopes, and incremental test risk reduction. Question 18. How would you formulate a trajectory optimization problem for an autonomous vehicle? I formulate trajectory optimization with vehicle states and controls over discrete time, enforce dynamics, and define objectives such as time, energy, smoothness, or tracking error. Constraints represent actuator limits, collision clearance, terminal conditions, and operating boundaries. Direct collocation is useful for nonlinear dynamics, while sequential convex methods can improve speed. I warm start from the previous solution, check feasibility, and execute the plan through feedback control rather than treating optimization as open loop. Discuss state and control variables, dynamics, objective functions, path and terminal constraints, obstacle avoidance, discretization, solver selection, feasibility, warm starts, and closed-loop replanning. Question 19. How would you tune a controller when the vehicle model is uncertain? I first identify which uncertainties matter most through sensitivity analysis, mass properties, aerodynamic coefficients, actuator delays, or sensor bias. I update the model using safe experiments, then design for parameter ranges rather than a single nominal case. Robustness margins, disturbance rejection, gain and phase checks, and Monte Carlo simulations reveal weak regions. I may add feedforward or adaptation, but I avoid complexity unless it produces measurable benefit and remains verifiable. In your answer, include parameter uncertainty, system identification, robustness margins, disturbance modeling, sensitivity analysis, Monte Carlo testing, conservative operation, and the role of adaptive or robust control. Question 20. Describe a difficult GNC debugging problem and how you would approach it. I would begin by reproducing the failure with the smallest scenario that triggers it, then compare commands, measurements, estimates, and actuator outputs against expected timelines. I would check units, frame transformations, timestamps, saturation, numerical values, and recent software changes before tuning anything. Logging innovations and loop rates usually narrows the fault quickly. After isolating the cause, I add a regression test, improve observability, and retest across nominal and off-nominal conditions. Focus on disciplined diagnosis. Reproduce the failure, establish expected behavior, inspect telemetry and timing, validate frames and units, isolate subsystems, test hypotheses, and document corrective and preventive actions. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.